So here you can see the main dashboard of HELINKS STS. You see a couple of buttons. These buttons more or less are the buttons according to the engineering process. So first of all we have the import button, which is used to import any kind of SCL files which are needed for the engineering. You can also use this button to import Excel sheets with signal lists. Then we have the single line button. This is how we do the specification. We have the system diagram. This is how we build the SCD file. When HELINKS has created the SCD file, it automatically also calculates the communication configuration based on the specification. So once this is done, you can use the communication editor to validate and verify the communication configuration, and you can also naturally adapt it and tweak it. Finally, there is the documentation button, which allows you to create project documentation, and then you can export everything using the export button that I'm showing here. So let us start now with the single line. So we do the specification. Here you can see the incoming feeder from our example. You also see a voltage level, G 20 kV, and a symbol for the substation itself. When I'm selecting the bay number 1, then I can do a right mouse click and say select children. Now the system shows me all the conducting equipments which are part of this bay number 1. So this editor is not just a graphical editor, it is a semantic editor. In the background, STS keeps track of the graphics and calculates the 650 SCL or SSD file. We can see this also when we select the voltage level G with select children. Now the bus bar is included in the selection. When I take the entire substation and say select children, then the entire or all the elements are included. Down here in the lower part of the screen we have a couple of tabs. There is one tab which is called the signal tab. This signal tab contains all the data that we need in the project. So data that we need is data that we want to communicate. Communicate to the network control center or the local HMI, or that we need for communication between the relays for goose messages. When I select, for instance, the QA0, the circuit breaker, then the system shows in this signal tab all the signals related to the circuit breaker. You can see user-defined names on the left. You see values for substation voltage bay, that is the 650 unique context for this data, and we see the 650 data representation, position, the operation command, the position value. We also have two columns, IED and logical device inst. These columns are empty. This is because we are currently in the pure specification state. So we do not have any IEDs related to our project. So everything what we're doing is specifying the system. We have additional fields down here with the HMI text. So as you see, this list goes beyond 61850. And at the end, we also have an indication about the communication. So we see that all these signals are currently destined to the network control center and to the local HMI. The engineering status specified is also shown in this column. This is in line with the specification state of missing the IEDs and the logical devices. Now all these logical nodes, which are part of this name and these signals, cannot be shown in the single line. This would overload the single line. That is why behind each of these elements in the single line, we have, just see if the audio is working. Yeah, we have a functional specification diagram. This functional specification diagram can be accessed by double-clicking these elements. So I make a double-click on the bay number 1, and the functional specification diagram of bay number 1 opens. On the left side we recognize the single line again. Now each element of the single line has associated a function. So I've selected right now the circuit breaker function named CBR/QA0. This circuit breaker function contains the logical nodes which are related to this circuit breaker. The logical nodes itself, I can select them, and you see that with the selection of the logical nodes also the signal list on the bottom changes. So whenever you are interested in the signals of an element, you just select the element and check the signal lists down here. So we have one type of functions which are related to the primary equipment, but we have also functions which are related directly to the bay, like the overcurrent protection function that we have here, or the tap changer function. These are functions which are coming from a library. Naturally, you can also create your own functions, including in these functions then logical nodes from different origins, for instance from edition 1 of the standard, from edition 2 of the standard, or from custom libraries that you define yourself. The last element that we have on this drawing are virtual IEDs. So the virtual IEDs here are the gray boxes that we can see. We have a bay control unit, a bay protection unit, and a tap changer. These virtual IEDs, even if we have an IED type here, this type is shown because in previous demos we had already assigned real types to this. But when I make a double click on this virtual IED, then there is no information available. So the reason that we have the virtual IEDs here is that they allow us to assign and to group the functions. So the connections between the functions and the virtual IEDs indicate that we are going to implement these functions in this box. This is the content of the bay number 1. Now we can continue with our project and adding some outgoing feeders here. Adding the outgoing feeder we do by creating a bay, and I'm selecting here the bay type line feeder. This bay type is instantiated, and the type serves as a filter for the functions which are available during the drawing of the bay. Before I add or complete a single line, I'm going to open the functional specification diagram of this bay. So I make a double click here. As we can see, the functional specification diagram is empty. I take the palette of the other side, the palette from the single line editor. And now we have a view where on the left side we see the single line diagram. On the right side we see the function specification diagram for the bay number 2. Now I'm taking care that the bay number 2 is the active bay. This is indicated by the blue point. So now every element that I'm going to add to the single line will be part of the 650 hierarchy of this bay. Let us start with the bus bar, with the disconnector, and here I'm selecting the direct operator disconnector, call it QB1, and you can observe now that on the left side in the functional specification diagram the QB1 appears also, but in addition we have the function added including the logical nodes and including the signals. I'm going to continue and adding the circuit breaker. Here we take a circuit breaker with select before operate. We call it QA0. Then we are going to take the current transformer, and here, because we are only measuring the currents, so I take the variant currents of the current transformer. Call it CT1, and yeah, we do not want to make a drawing exercise, so I close the example by adding a feeder. Finally, I do the electrical connections. Without the electrical connections, the SSD file will not be valid. And then we are done with the primary part of the single line, so we can close the single line editor. And I'm shifting the specification to the main window. And in the main window, we see now on the left side the single line diagram, and here we have the functions. I'm using the auto layout to arrange the functions. And then we have the primary equipment related functions. So next we will add the time overcurrent function, protection function from the library, and we will add our IEDs. So here I take the bay control unit, name it PCU. I take also another bay control, another IED, name it BPU for bay protection unit. Obviously the bay controller will implement the control functions. And we are using also the bay controller to implement the measurements, because the MMXU logical node here is used for the monitoring of the currents and voltages case. The relationship of the CT with the protection function is not shown here on this level. So we assign the time overcurrent protection to the bay protection unit, and somehow implicitly we know that the relay is configured in a way that the PTOC will be working with the current from the CT. Arrange again, and now we are finished with the static part of this bay. Just a short look at the signal list. I'm going to double click on the signal list, which makes a signal list taking place of the entire screen. And we can see that now in our bay 2 we have a couple of functions and a couple of related signals. We have commands, status, and also measurements. So the double click, I come back, and now I'm closing the bay number 2, and we are back on the single line. The next step is we need more than one outgoing feeder. So I'm selecting the bay number 2 and use the copy function. Control V, I can paste, and I can paste once more. Now we have 3 outgoing feeders. I'm going to rename these feeders, the bay number 3 and the bay number 4. Finally, I connect them to the bus bar. A short check on our signal list. Let us see that now we have in this signal list, I have to going to select the substation. Now in the signals we have the signals of bay number 1. They were already there at the beginning. We have the bay number 2, we have the bay number 3, and we have the bay number 4. So we have a nice bunch of signals right now available here. Yeah, to make it nicer, maybe we have here also different feeder names. And now we are done with the static part of this specification project. Next step is that we are going to add the specification for our communication needs. So we will specify which signals we are going to send to the network control center and to the local HMI, but we also will implement, or we will specify the communication for our protection function, the simple busbar protection, where we are going to send one goose message from each of the outgoing feeder to the incoming feeder in order to block the protection function there. But let us start with the vertical communication. In 61850, the clients are represented by client logical node from the interface class like ITCI or IHMI, and these client logical nodes are allocated to the physical clients, to the gateway computers or whatever is client. Here in our example, I make a double click on the functional specification of the substation, and we come here to the functional diagram on substation level, and we see we have one placeholder for a gateway, and this gateway implements two functions, the network control center communication function and the HMI function. They both have an interface logical node, and what we are going to do, we are now collecting all the signals that we intend to send to these interfaces. So I'm clicking here on the ITCI and say configure inputs. Now we get already a couple of signals here. I think this was from the previous demo. Let me remove them and we start. So we make a select. Now we have a tree view on our system, and in this tree view we see the voltage level G, we see the bus bar, the bay number 1 which was already there, and the 3 bays that we have created. We could drill down now and find the signals we are interested in, but because as I've explained at the beginning, the signal list in this project comprises only the signals that we need for communication, so it does not contain all the 61850 signals defined by the standard. It comprises only what we need, so we say let us take all the signals of voltage level G. MMS reporting can be buffered or unbuffered, or it can so you can configure this here, but you can also use the functional constraint depending checkbox. This will allow HELINKS to decide about buffered or unbuffered. Status values will be sent in the buffered report, measurements will be sent in an unbuffered report. We say OK, and now we have here a list which contains all the signals that are intended for the network control center. You see there are also commands, so it is both directions, and we have status and measurements. So this is not a data set, but it is used by HELINKS to calculate the data sets. This list also can be used when we export it in Excel in order to configure the gateway computer. So now I say OK, and we are done with the MMS reporting for the control center. We do the same for the local HMI, and also here we remove the existing one, we select what we want, and we take again just everything. And the second channel for the HMI is also configured. So this was everything what we need to do for reporting. In the next step, we are going to create some goose messages. In order to do this, I open the application drawer and I'm selecting a goose application. This goose application, I call it reverse blocking, because we are going to block the incoming feeder backwards from the outgoing feeders. Before I open the editor of this goose application, I'll create a documentation link between this box and some predefined documentation that I have in my workspace. So I'm going to a doc folder, applications, and there is a document which is describing this reverse blocking scheme. And I'm adding this document, and you will see later when we create the PDF documentation for our project why I did this and what it will contribute to the project. So now I'm going to open this application, and because we do not have any IEDs, we cannot send a goose message from one IED to another IED. But what we can do, we can send a message from one function to another function. So we go here to the sending functions, and now the system shows us a dialog where we see all the bays. So we want to block from bay number 2 and 3 and 4. So we need to send from the bay number 2 from the overcurrent protection function. So which signals are we going to send? Make a right mouse click on this function. And now the system shows us a selection of the logical nodes that we have in this and the list of signals that we have that we are using in these logical nodes. And now we are going to select time overcurrent PTOC1 general start, and that's it. This is the goose publishing for the bay number 2. We do the same for the bay number 3. Also defining the signal. And also for the bay number 4. Yeah. This is all we need to do for goose publishing. Now goose reception. The same principle. We want to receive this message and we want to block in the bay number 1 the overcurrent function. So we select this function. We select here a high priority connection. This will influence the minute max duration time of the goose message later on. And we drag here. And now the system shows us the logical nodes in this protection function. We select the PTOC because that is the one we want to block. And this PTOC, yeah, we define a placeholder for the input signal, plug in 1, or just name it block 1. And I do the same for the other two, and also here I'm defining a new input. It is also possible to define these inputs before using before creating the goose messages, and to have these inputs also as part of the library, as part of the predefined solution. Then they show up directly and you can use it. So now we are done with the goose messages. Once we have IEDs in the system, HELINKS will automatically, after the appropriate mapping of the logical nodes, calculate the goose messages and create, for instance, external reference entries, so goose subscription entries based on the inputs that we have defined here. I'm closing this editor, and now we are done with the specification. So normally we would create now the SSD file, the documentation, maybe the signal list and so on. But I will not do this right now. At the end of the demo we will see how the documents are generated. So now let us switch the head and let us do the system integration. That means we have to bring in now IEDs into the project. If we look here on the navigator window, in the left lower part, there we have a folder which is called STG. This folder contains ICD files, capability descriptions of IEDs. And these are ICD files from a couple of different vendors. It is Schweizer, GE, ABB, Siemens, and so on. When the system starts up, it will read this directory and make these ICD files available in the project for instantiation. We can see this in the system diagram. So now I'm going to switch to the system diagram. And the system diagram that you can see here is our representation of the SCD file. The ICD files on the left side, they show up in the palette of the system diagram here on the right side. So for instance, when I open here the Siemens palette, then we see a Ciprotec 7 SJ6, which is based on the ICD file in the folder that I just showed. So if you look at the content of our SCD file, then we can see that we have 3 IEDs for the bay number 1, G01 BCU and so on, 2 for the bay number 2. In the bay number 3 and 4, we have 2 IEDs missing. In the bay number 3, we are missing the bay controller, and in the bay number 4, we are missing the bay protection unit. So let us take this Siemens here and instantiate it. So now we have created an ICD file template which has been produced by the manufacturer's ICT tool. And based on this template, we create a new instance of the IED in our project. And we name it G03 Bay Control Unit. We connect it to the switch. This will create a subnet entry connected access point in the SCD file. Then we go to the ABB drawer and we take an ABB 630 that we put here in the drawing, and we call it G04 Bay Protection Unit. And we connect it to the network. So now we are done with the SCD file. From this SCD file we can access each detail of the SCL representation. I do not go into this, there we will have a separate, maybe a separate session for this. But currently this SCD file here, this configuration, has nothing to do with the single line from our specification. So the task that we have to do now, it's manifold, it's 2 things. First, we need to associate all the elements with the single line. That means the virtual IED and the real physical IED needs to come together. For each logical node that you have the specification, we need to select the appropriate logical nodes, which are the implementation here in these relays. And we need to make sure that each signal that we have specified is also available in these IEDs. This can be a very lengthy process, but based on the libraries and some naming rules that we have here, we will be able to perform this task with a single mouse click. Once we have brought everything together, in the last step we need to configure the SCD files so that it represents all the communication that we have specified. So we need to configure the datasets for the report and the datasets for the goose, and we need to associate the appropriate control blocks or even create these control blocks. These are the two tasks that we are going to perform now. In order to do this, I'm switching back to the single line diagram and I'm showing you two bays. I'm showing the bay number 2 and let's say the bay number 4. I show them beneath each other. We're splitting the screen. So we see on the left side the bay number 2 and on the right side we see the bay number 4. Now we have a button here on the top which is called Implement Virtual IEDs of Specification with the IEDs from the SCD file. With this button we can associate the real IEDs with our virtual IEDs. Maybe you have seen that the names of the real IEDs are close or are derived from the substations here, substation values. So we have the voltage level value here, we have the bay number, and this shows also up in the names of the relays. That is why HELINKS can automatically assign these bays. So I'm clicking on this button, and you see that now the shape or the color of this IED elements is changing. We have a green hook here, and we see that now our bay protection unit in bay number 4 became a IED 630. That the controller is a Schweizer relay. If we go to our bay number 2, we have an Alstom and we have a GE. This is not the only thing that changed. We see also that the logical nodes have changed. The small chain element which is in front of the logical node is closed now. This means that we have implemented this this logical node with a logical node coming from the IED. If we look here in the bay number 2, this worked fine except for the MMXU. So somehow we have not associated the MMXU. So why not? Let us check. First I look at this MMXU, make a right mouse click and show type mappings. Now I can see all the relay types that this relay is knowing, or this logical node is knowing, and we see that it doesn't know a C60. That means we have here a D60, but we do not have a C60 from GE. So obviously we need to teach this logical node how to work with a C60. I make a double click, and now we see the content of this relay, and I'm going to the metering, logical device, and here I'm selecting the first MMXU and assign it to this relay. And now we see that also this logical node here is satisfied. If you have a look in our signal list, then we can also see in the signal list that now this IED shows up. And this is the same for all the other IEDs. or the other signals, signals show up. If I take this relay away with virtualization, the elements go back in their original state. And just now, before I forget it, I'm updating the library with this changed function. And the next time I do the project, this logical node will automatically find the connection with the proper logical node in the relay, as I did right now. We have another point. We look here on the right. There we see some red error messages. Let us just check what it is. I'm going here to this XSWI, and we have a look at the signals. There we see that all the signals are implemented as specified, but one is unresolved. So the EE health is not available in this Schweizer relay. And the same, if we are looking here at the CSWI, there we have the position operation is implemented, but the select before operate is unresolved. So obviously the Schweizer relay does not support all the signals here that we have specified. In this presentation I will not continue with solving this, but there are means that HELINKS supports you to solve this. Either you change something in the IED, where make new logical nodes which support these signals, or we are going to use different logical nodes to implement it in these signals. And the same is here for the ABB, where we also have one signal which is not implemented. For now, I do not change, do not fix these issues. Now we just continue, and we are aware that we have some inconsistencies and some incompleteness in our project here. The next step, after associating all these signals and logical nodes, maybe we can have a very short look on our signal list right now. And in the signal list we see that most is implemented as specified, something are implemented differently, something are unresolved, very few things are open. So for now we are happy. Now the next step is that we need to implement the communication configuration based on our specification. Now when everything is associated, HELINKS can do this automatically. HELINKS can automatically create datasets, control blocks and other values, and it is done by using this button here, Set SCL Communication Settings from Specification. I'm clicking on this button, and here is a dialog which allows different operations. For now we just configure the communication, and we configure everything. We make sure that we configure all IEDs and say OK. Now this is running, and it completes with a couple of errors. Let us have a look at these errors. And now we see that some signals are not resolved. For instance, here we have the select before operate, position select before operate, or the eHealth. So obviously a couple of signals that we want to communicate are not available. If we check this, these error messages will correspond exactly to the problems that we have in the implementation. So we are now okay with this, and now we are done with the project. Now we just have to export the SCD file and do some documentation. Let us start with the SCD file. Clicking here on the SCD, and you see here a list of elements that we are able to export. And I'm selecting goose matrix, so we will have an Excel representation of our goose messages. I'm selecting an Excel sheet with the communication configuration. There we'll have an overview on the data sets and report control blocks. And naturally we want to export an SCD file. We include the substation section. We export edition 2. and we suppress empty control blocks. This is quite a good default setting, and we say OK. Now this is running. Because we have a mix of edition 1 and edition 2 relays, we get a warning here which is complaining about a couple of things, but this is normal in a mixed system. And now export successfully completed, so we can have a look at the SCD that has been created. We go to the out folder. In the out folder we see an SCD file, multi-vendor SCD, and it has been created at 5:30 p.m. so that is the current time of the demo here. I make a right mouse click, open it with an XML editor, and we see the SCD file. It has a substation section, it has a couple of IEDs included. We can search here for the inputs section. Yeah, so too far. I wanted to show the inputs of the ABB relay. Okay. We'll see them later on in the PDF documentation. So here I'm clicking on the button for the documentation and exporting the creating a PDF documentation of our project. So first it is extracting all the pictures and tables, and then it is rendering it in PDF. And now I have to switch the application that I'm sharing. You should be able to see it right now. It's a PDF file. I'm drilling down. We have a table of contents. We have an introduction. Some chapters I have not shown how to add them. Now here we have a general specification chapter, and maybe you remember the reverse blocking scheme that we created. The content that you see here, that is the reference to the document that I added to the reverse blocking. Then we have a chapter about functions, and you see that the collection of functions here corresponds to our functions in the specification. We have the line disconnector, the circuit breaker with select before operate, the time overcurrent protection. So each of these functions that we have taken from the library has also associated a document which can be edited with Word, and these pieces of document, they are assembled here in this project report. So then we have our single line, we have the application that we created, we have signal lists for each of the bays, and if we are interested in a little bit more detail, for instance, we want to understand the 61 and 50 meaning of these data attributes, we can make a click here on the description of the signal, and we come to the glossary where all the 650 attributes which are used in the project are described. Finally, we have the SCD specific part of the description. So we see the overview diagram, we see all the IP addresses and the list of relays, and finally we have a detailed listing of all the report control blocks, the parameters, and the dataset contents. And at the very end of this We also have the chapter with the goose messages, and we see that we have 3 goose messages defined. The publisher is domain number 3, 4 and 3, 2 and 4. We have some goose configurations, and the subscriber is the IAD in domain number 1. And again, all the parameters of the goose messages and the content of the dataset. So with this, we are done with this example. And in the last hour, what we have done is we have nearly from scratch, based on an application library, created a complete substation project. We have done the specification in 61850. We have added relays from 4 or 5 different vendors. We have configured goose control blocks. We have configured datasets for about 100 of signals. And we have created the SCD file and the comprehensive PDF documentation. And with this, we are at the end of this demo. There were a couple of open points, how to deal with errors and inconsistencies. And surely there are also other questions, so please feel free to contact us for further information. Thank you very much.